Welcome to the deep dive. We're tackling a core software design pattern today, one that's all about keeping different parts of your system singing from the same hymn sheet without being, so tightly linked they trip over each other. If you're aiming for a senior software engineer role, understanding this pattern and its nuances is seriously valuable for showing you get robust and scalable design.
Absolutely. We're going to dig into a pattern that manages a one-to-many relationship between objects. Think of like a central piece of information that many other parts of the system need to react to.
Right.
This pattern provides a clean way for those dependent parts to be notified automatically whenever that central information changes.
Right. It's like those airport departure boards, isn't it? Multiple screens all over the airport need to display the latest flight information. The airline updates its central system, and bang, all those screens refresh.
Exactly.
The screens don't need to constantly, poll the airline's database, and the airline system doesn't need to know about every single display screen out there.
Precisely. Our goal today is to really grasp the fundamental pieces of this pattern, how they interact, and what makes it such a powerful tool in software architecture. This will definitely give you some strong material to draw on when discussing design principles in your interviews.
Okay, let's unpack this then. What's the core problem this pattern is really trying to solve at its heart?
Well, the fundamental challenge is maintaining consistency among related parts of a system without creating what we call tight coupling.
Tight coupling.
Yeah. When components are tightly coupled, they become very reliant on each other's specific implementations, which makes it much harder to modify or reuse them independently.
Right, brittle.
Exactly. Imagine our airport example again. If the departure board software was directly tied to the airline's specific database structure, any change on the airline side could break all the display screens. The observer pattern helps avoid this kind of fragility. Think also about a spreadsheet application where multiple charts are visualizing the data. When the underlying data changes, the charts need to update, right?
Yeah, immediately.
But ideally, the charts shouldn't have intimate knowledge of the spreadsheet's internal workings.
That makes a lot of sense. So how does this pattern achieve that necessary distance while still ensuring everyone who needs to know gets the update?
It introduces two key players: the subject and the observer.
Okay.
The subject is the object that holds the important data, the state that other objects are interested in. It provides a way for other objects, the observers, to register their interest, to essentially say, hey, let me know when this changes.
Like subscribing.
Exactly like subscribing. The subject is also responsible for then notifying all those registered observers when its state does indeed change. It's a bit like having a central announcement system.
And the observers, what's their role in this dynamic?
The observer defines a contract, typically an interface, that says, I know how to update myself when something I'm interested in changes. This contract usually includes an update method, right?
The method.
Yeah. Any object that wants to be informed by a subject must implement this observer interface. When the subject changes, it iterates through its list of observers and calls this update method on each one.
Okay.
The observers can then, in response, take whatever action they need, often by asking the subject for the new data to refresh their own state or maybe their visual representation.
Okay, so we have these two key roles with their defined responsibilities. How would these translate into actual code in terms of structure and relationships?
We can visualize this with UML class diagrams, though we won't show them here. Picture an interface or an abstract class called subject. This would define the basic operations: a way to attach observer, to add an observer to its internal list.
The subscribers.
Right, the subscribers, the interested parties, a way to detach observer, to remove one when they no longer care, and a crucial notify method. The notify method is where the subject iterates through its list of attached observers and calls the update method on each one. It doesn't know the specifics of what each observer will do. It just tells them that something has happened.
Got it. So it's broadcasting. And on the receiving end, what does the observer look like in this structural view?
On the other side, we have an interface or an abstract class called observer. This interface defines that single but vital method, update.
Just update.
Just update. Now, to make this concrete, we'd have a concrete subject class. This class would implement the subject interface and hold the actual data, let's call it subject state.
The actual value.
Yeah, actual value. It would also have methods to get and set this state, get state and set state. Critically, within the set state method, after the subject state is modified, it would typically call the notify method to alert all registered observers about the change.
And then the actual objects that want to react to these changes would be the concrete observer classes. They implement the interface.
Exactly. A concrete observer is a class that implements the observer interface. It will have its own internal state, perhaps a cached copy of the data it's tracking, let's say observer state.
Okay.
When its update method is called by the subject, this concrete observer will then usually call the getState method on the concrete subject to get the latest data and update its own observer state. It might also hold a reference back to the specific concrete subject it's observing.
Okay, I think I'm starting to get a clear picture of the static structure. Now, how does this all unfold when the application is running? What's the sequence of actions when a change actually occurs?
Right, the runtime. We can illustrate this maybe with a mental sequence diagram. Imagine we have a specific instance of a concrete observer, let's name it listener 1, and an instance of our concrete subject called data provider.
Okay, listener 1 and data provider.
The sequence might begin when some part of the system, perhaps through user interaction or an external event, calls the setState method on data provider. This triggers a change in the data provider's internal data.
And then data provider, realizing its data has changed, does what?
Correct. Inside the setState method, data provider then invokes its own notify method. This notify method then goes through its internal list of registered observers. For each observer in that list, including our listener 1 and perhaps another one, listener 2.
Could be many.
Could be many, yes. The data provider calls their respective update methods.
So the data provider essentially broadcasts a, hey, something changed message to everyone who has signed up. That's the core idea.
In this basic form, yes, that's the essence. And in response to receiving that update call, each observer would then typically call the getState method on the data provider to retrieve the actual updated information.
Pulling the data they need.
Right, pulling the data. They then use this fresh data to update their own internal variables or refresh whatever they were displaying to the user, like our spreadsheet and chart example we talked about earlier.
Okay, that step-by-step runtime view really clarifies things. So what are the significant advantages we gain by employing this observer pattern in our designs? What are the big wins?
There are several compelling benefits. The first, and maybe the biggest, is abstract coupling.
Abstract coupling.
The subject only knows about the abstract observer interface. It doesn't have any knowledge of the concrete classes of the observers that are registered with it.
Doesn't care what they are, just that they can update.
Exactly. All it knows is that they have an update method. This minimal coupling is incredibly valuable for software reuse. You can reuse the subject in different contexts with different sets of observers without them being tightly intertwined. They can even exist in complete different modules or layers of your application, promoting a more modular and maintainable architecture. It's like designing components with well-defined interfaces that allow them to work together without needing to know the intricate details of each other's implementation.
That sounds like it could really simplify the evolution of a larger system. What's another key advantage?
Another major benefit is broadcast communication.
Okay.
When the subject state changes, it automatically sends a notification to all its subscribed observers without needing to know who they are or how many there are.
Fire and forget, almost.
Kind of, yeah.
Yeah.
This allows for a very dynamic system where you can add or remove observers at runtime without modifying the subject at all. It's up to each individual observer to decide how it will react to the notification. This is particularly useful in UI development, where you might have multiple views that need to reflect the same underlying data.
Right, like different charts for the same spreadsheet data.
Exactly. You can add new types of visualizations without touching the data model itself.
So we can essentially plug in new ways of reacting to data changes without having to modify the core data handling logic. That sounds powerful.
Precisely. This leads us to the third important advantage, independent variation. Because the subject and observers are so loosely coupled, you can modify and reuse them independently. You can introduce new types of observers without needing to change the subject or any of the existing observers. This greatly enhances the flexibility and extensibility of your system over time, making it easier to adapt to new requirements or integrate with other systems.
These all sound like significant wins for building flexible and maintainable software.
Yeah.
But are there any potential downsides or challenges we should be aware of when considering the observer pattern? No silver bullets, right?
No, definitely not. There are certainly potential liabilities to keep in mind. One is the risk of unexpected updates, which can sometimes lead to cascading effects.
Cascading effects.
What do you mean?
Because the observers are unaware of each other, a seemingly small change in a subject could trigger a chain reaction of updates across multiple observers.
This could potentially lead to significant performance overhead or unintended side effects that can be difficult to trace and debug. Imagine a complex system where one data change triggers multiple UI updates, and one of those UI updates then triggers further data processing and so on. It can become quite a tangled web if you're not careful.
That makes sense.
Mhm.
If one notification triggers a series of other actions, it could become hard to manage. What else should we be careful about?
Another potential pitfall is spurious updates.
Spurious, meaning unnecessary.
Exactly. If the criteria for when a subject should notify its observers aren't carefully defined or maintained, it can lead to unnecessary update notifications being sent out, even when the underlying state hasn't actually changed in a way that warrants an update. These spurious updates can waste system resources and make it harder to pinpoint the real cause of issues. For example, a sensor might send out a notification every few milliseconds, even if the measured value remains the same. All the observers receiving these notifications would then have to wake up, maybe query the subject, and check if anything has actually changed. Bit wasteful.
So it's crucial to be precise about when a notification is truly necessary. Don't just notify on every tiny internal fluctuation.
Absolutely. And finally, the basic update method in the observer interface often doesn't provide much detail about what specifically changed in the subject.
Just something changed.
Pretty much. This can force the observers to do extra work to figure out what they need to update. For instance, an observer might have to requery the entire state of the subject even if only a small part of it has been modified. This can be inefficient, especially if the subject holds a large amount of data.
Okay, so we've looked at the advantages and the potential drawbacks. Now let's consider how this pattern is actually implemented in practice. Are there different approaches or key decisions developers need to make during implementation?
Yes, there are several important implementation considerations and variations. For example, how does the subject actually maintain the list of its observers?
Right, the mechanics.
The most common and straightforward approach is to use a simple list or collection, like an array list in Java, or a vector in C++A, to store references to the registered observer objects.
Seems simple enough.
It usually is. However, in scenarios where you have a very large number of subjects, but relatively few observers interested in each one, you might consider using an associative data structure like a hash map.
A map. How would that work?
Well, the map could potentially map subject identifiers to lists of observers, or maybe use weak references. The idea is it could be more memory efficient as you potentially only store mappings for active relationships, although it might introduce a slight overhead in terms of the time it takes to access the observers during notification.
Okay. So it's a trade-off between memory usage and access speed.
Exactly. That's an interesting optimization to consider in specific, maybe large-scale scenarios.
What's another implementation detail that comes into play?
Another key point is whether an observer needs to be able to observe multiple different subjects.
Oh, right. Can one observer listen to many subjects?
Yes, absolutely. In a complex application, it's quite common for a single object to be interested in changes in several independent data sources. In such cases, the update method in the observer interface might need to be extended.
How so?
It might need to include a reference to the specific subject that triggered the notification as a parameter. So, update subject changed subject.
So the observer knows who is calling.
Precisely. This allows the observer to determine which subject has changed and react accordingly, perhaps retrieving data from different subjects based on the notification source.
That makes sense for more intricate scenarios where a single component might be aggregating data from various sources.
Yeah.
Now, who is actually responsible for initiating the notification process? Is it always the subject itself, like in the set state method?
Not necessarily. There are two primary approaches here. The first, and perhaps the most common, is what you just described. Have the subject call its notify method as part of its state-modifying operations.
Seems logical.
Yes. For example, within the setState method, after the subject's internal state has been updated, it would then trigger the notification to all registered observers. This is convenient for clients of the subject, as they don't need to remember to initiate the notification themselves.
But I sense a but.
Well, the but is if a client makes a series of rapid successive changes to the subject's state, this approach can lead to multiple, potentially redundant notifications being sent out. Think about dragging a slider. You might get dozens of updates before the user starts.
Right. A flurry of notifications, even for intermediate states that the observers might not actually care about until the final change is made.
Exactly. That can impact performance. The second approach is to shift the responsibility for triggering the notification to the client that modifies the subject's state.
So the caller of set state also has to call notify.
Yes. In this model, the client, after making the necessary changes to the subject, would explicitly call the subject's notify method. This gives the client more control and allows for batching of updates.
Okay.
For example, a client might make several changes to the subject and then call notify only once after all the changes are complete.
That sounds more efficient in some cases.
It can be. The downside here is that it places an added burden on the clients, and there's a risk that they might forget to call notify, leading to inconsistencies where observers are not informed of changes. It's less foolproof.
That sounds like it could introduce subtle bugs if clients aren't diligent. What other implementation challenges might developers encounter?
Dealing with dangling references is a critical concern.
Dangling references, meaning pointing to something that's gone.
Exactly. When a subject object is no longer needed and is about to be destroyed or garbage collected, you need to ensure that any observers that were registered with it no longer hold references to it.
Why is that so critical?
Holding on to a reference to a deleted object can lead to crashes or other unpredictable behavior when the observer tries to interact with it, maybe during its update method. A good practice is for the subject to notify its observers when it is about to be removed, giving them a chance to detach themselves or reset their references. Simply relying on automatic garbage collection might not be sufficient, especially if the observers have a longer life cycle than the subject they were observing.
That's an important point about managing object life cycles carefully in these relationships. What about the internal consistency of the subject state when it does notify?
Ah, yes, absolutely vital. It's crucial to ensure that the subject's internal state is in a consistent and valid state before it calls the notify method.
Why before?
Because observers will often query the subject for its current state as part of their update process. Get state, remember. You don't want them reading incomplete or inconsistent data if the subject is, say, in the middle of a multi-step state change.
Right, like if it updated X but not Y yet, and the observer needs both.
Precisely. Using template methods within an abstract subject class can be a helpful way to enforce this. You can define a template method that outlines the steps for a state change, ensuring that the notification to observers happens only as the final, consistent step.
That sounds like a good pattern within the pattern to maintain data integrity. Now, we briefly touched on the amount of information shared during the notification. Can you elaborate on the push versus pull models in more detail?
Certainly. This is a key design choice. In the push model, when the subject notifies its observers, it also sends detailed information about what has changed, or maybe even its entire current state, as arguments to the update method.
So, update value 1, value 2.
Right. While this can be convenient for the observers as they receive all the information they might need directly, it can also make them less reusable. Why? Because the subject might end up making assumptions about what information all its observers need.
Assumptions are often bad.
They can be. If the subject later decides to send more or different data, all the observer's update methods might need to be modified, even if they only care about a small subset of that data. This can lead to tighter coupling in a different way, ironically.
So the subject is kind of dictating what the observer should be interested in, almost forcing data on them.
In a way, yes. In contrast, the pull model is more minimalist. The subject sends a very basic notification, essentially just signaling that something has changed. Maybe update takes no arguments or just a reference to the subject itself.
Okay.
The observers then, in response, explicitly request the specific data they're interested in from the subject using its getter methods, get state, get temperature, etc.
The observer takes charge of getting what it needs.
Exactly. This approach emphasizes the subject's complete ignorance of the observer's specific needs, which generally leads to more reusable and adaptable observers. However, it can be less efficient if the observers need to make multiple calls to the subject to retrieve all the necessary information to update themselves.
Right. Potentially more network traffic or method calls.
Correct. It's a trade-off between the convenience and potential efficiency of the subject, providing everything upfront, push, versus the flexibility and adaptability of observers only asking for what they need, pull, potentially at the cost of more requests.
So a choice between immediate convenience and potential inflexibility versus more work for the observer, but greater adaptability. It depends on the context, I guess.
It really does depend on the specific needs of the system. Another refinement related to this is the idea of specifying modifications of interest, sometimes referred to as aspects.
Aspects, like filtering the notification.
Kind of. Instead of just a general notification, observers can register their interest not just with the subject, but for specific types of changes or specific parts of the subject state.
How would that work?
Maybe the attach method takes an extra parameter, like attach observer, aspect of interest. When one of those specific aspects changes, the subject only notifies the observers that have registered interest in that particular type of modification.
Ah, I see.
This can significantly improve efficiency by avoiding unnecessary notifications to observers that wouldn't be affected by a particular change. For example, in our weather station, a display might only care about temperature changes and not humidity or pressure. It would only register for temperature aspect updates.
That sounds like a much more targeted and efficient way to handle notifications, especially if updates are frequent or expensive to process. What happens when the relationships between subjects and observers become very intricate and complex? Lots of dependencies.
Right. In scenarios with very complex dependencies between subjects and observers, simply having subjects notify observers directly can get messy, potentially leading to those cascading updates or redundant notifications we mentioned. In these cases, you might want to consider introducing a change manager or a similar mediator object.
A change manager, what does that do?
This object acts as a central hub for managing the relationships and orchestrating the update process. Its responsibility is to ensure efficient and consistent updates across the system.
So instead of subject observer, it's subject change manager observer.
Essentially, yes. The subject tells the change manager it has changed. The change manager knows which observers depend on that subject, and maybe others, and figures out the best way to notify them. For example, if an observer depends on multiple subjects, the change manager can ensure that the observer is only updated once, even if multiple of its dependent subjects change around the same time, thus preventing redundant updates.
So it's like a traffic controller for updates in more complicated scenarios.
Yeah.
Debouncing or coalescing updates.
Yes, precisely. It centralizes that logic. There are different types of change managers, too. A basic one might simply forward notifications. More sophisticated ones, like a hypothetical DAG change manager designed for directed acyclic graph dependencies, could handle more complex scenarios where observers might depend on other observers, forming a graph of dependencies.
Wow, okay.
The change manager could then ensure that updates happen in the correct topological order and potentially detect or avoid cyclical dependencies. This change manager concept is closely related to the mediator pattern, by the way. And often, you might have a single instance of the change manager for the whole system or a major subsystem, making the singleton pattern a relevant implementation choice for the change manager itself.
Interesting. So it seems like there are many ways to adapt and extend the core observer pattern to fit specific architectural needs, from simple lists to complex mediators. Is there any other fundamental implementation consideration we should touch on before the example?
Just one final point, perhaps a bit historical but still relevant depending on the language ecosystem. It's about how the subject and observer roles are handled in programming languages that don't support multiple inheritance, like classic Smalltalk or even Java before default methods and interfaces became common.
Right, you can only inherit from one class.
Exactly. In such cases, it's not uncommon to see the subject and observer interfaces or their functionalities combined into a single base class or handled through composition and delegation. The key is finding a way for an object to potentially act as both a subject, managing its own state and notifying others, and an observer reacting to changes in other subjects without needing direct multiple inheritance of implementation. Modern languages often offer more flexible solutions here.
Okay, we've covered a significant amount of ground, from the core concepts and structure to the benefits, drawbacks, and various implementation strategies and trade-offs.
Yeah.
To really solidify this understanding, can we dive into that concrete example we mentioned earlier, the weather station scenario?
Absolutely. The weather station is a classic, almost textbook illustration of the observer pattern in action. It makes the concepts very tangible.
Great, so set the scene for us.
Okay. Imagine you have a weather data object that serves as our subject. This object is responsible for tracking the current weather conditions. It holds the current measurements for temperature, humidity, and barometric pressure.
Got it. The source of truth for weather data.
Exactly. And it would implement the methods defined in our conceptual subject interface, register observer, to allow other objects to subscribe for updates, remove observer, to unsubscribe, and importantly, notify observers to broadcast the changes when new data comes in.
And then we have various display elements that need to show this weather information in different ways, like on different screens or widgets.
Precisely. We would define an observer interface, perhaps with an update method, Let's initially imagine a push model, so maybe the interface is update, float temp, float humidity, float pressure.
Okay.
Then we'd have concrete observer classes. For instance, a current conditions display that just shows the latest numbers, maybe a statistics display that calculates and shows average, minimum, and maximum values over time, and perhaps a forecast display that tries to predict future conditions based on current trends.
Different ways of looking at the same data.
Exactly. Each of these display classes would implement the observer interface to receive the updated weather data. They might also implement a separate display element interface, maybe with just a display method, to encapsulate the logic for actually showing the information to the user.
So when the weather data object gets new readings from its sensors, maybe a method like measurements changed is called internally, which then calls notify observers. And then the update method of each of these display objects gets invoked.
That's the core mechanism, yes.
Huh.
In our initial push model example, the weather data object within its notify observers method would iterate through its list of registered observers and call update, current temp, current humidity, current pressure on each one.
Pushing all the data out.
Right. And as we discussed earlier, this highlights the potential inefficiency. The current conditions display might only need temp and humidity, but it still gets the pressure pushed to it. The statistics display needs all three, perhaps, but the forecast display might have different needs again.
Which leads back to the pull model as an alternative.
Exactly. This scenario nicely illustrates why the pull model could be more flexible and potentially more efficient in the long run. In a pull model, the weather data objects notify observers might just call a simpler update method, maybe passing itself as reference. Update this weather data. Each observer would then explicitly call methods like get temperature, get humidity, and get pressure on the provided weather data object reference to retrieve only the specific data it actually needs.
Okay, that makes the push-pull trade-off clearer in context.
Can you give us a brief sense of what the code structure might resemble for some of these key components, say in Java-like pseudocode?
Certainly. The subject interface would just declare the register observer, remove observer, and notify observers methods, sub interface, subject void register observer, observer O, void notify observers. The observer interface for our push example would declare the update method, .java interface, observer, float temp, float humidity, float pressure. And maybe a display element interface, display element void display. Simple interfaces. And the weather data class, our concrete subject, how would that look?
The weather data class would implement subject. Internally, it would have private float variables for temperature, humidity, pressure, and crucially, a collection, like an array list observer, to hold the registered observers. AVA class. Subject, private array list observers, private float temperature, private float pressure, public weather data, public void register observer, observer O, observer O, observer O, observer O, public void remove observer, observer O, May observer O, A Jonah observer, observer. 4. Observer.update, temperature, humidity, pressure, push model. 4. Observer, called when new measurements arrive. 4. Observer, cust float temperature, float humidity, float pressure. 4. Observer, measurements get temperature, notify temperature. Observer, float temperature, observer pressure, observer measurements changed. Public measurements changed. For observer, set temperature, observer, return temperature, set for model. Concept getters for pull model would go here too. An observer, putter vario for observer temperature.
Okay, so set measurements updates the values and then triggers measurements changed, which calls notify observers, which loops through and calls update on each observer. Clear flow.
Exactly.
And a concrete observer, like our current conditions display.
Right. The current conditions display class would implement both observer and display element. Its constructor would typically take a reference to the weather data object, the subject, and immediately register itself. Java class current conditions display implements observer display element, private float temperature, private flow humidity, private subject weather data, reference to subject public current conditions display, subject weather data.register observer, this public void update, float temperature, float humidity, float pressure, this dot humidity, float temperature have it, this humidity temperature, update display when data changes. System.out.println current conditions, system.out.println current conditions, howit.println current conditions.println current conditions .pat.println current conditions, system.out.println current conditions last byte.
So the constructor subscribes. The update method saves the push data and calls display. The display method just prints it out. Makes sense.
That's the essence of it.
And to see all of this in action, we'd have a main application class or a test harness, right?
Exactly. A weather station main class, perhaps? It would first create an instance of the weather data object, our subject. Java public class, weather station, public static void a mood, main string args. Weather data, it was new weather data. Creates subject, then it would create instances of our concrete display observers, current conditions display, statistics display, forecast display, passing the weather data object to their constructor so they can register themselves. Java current conditions display, current display was new current conditions display, weather data, statistics displays, forecast display, forecast display, new forecast display, weather data. Finally, the test class would simulate changes in the weather by calling the set measurements method on the weather data object with different temperature, humidity, and pressure values. Java weather data.set measurements 80, 65, 30.4F, weather data.set measurements 78, 90, 29.2F. Each time set measurements is called, the notification mechanism we outlined would kick in, and all the registered display observers would automatically receive the updated data via their update methods and refresh their displays accordingly. You'd see the output from each display's display method appear on the console.
That weather station example provides a really clear, practical picture of how the observer pattern functions in a real-world context. It ties all the concepts together nicely.
Yeah, it's a good one for demonstrating the core mechanics.
So as we wrap up our deep dive, what are the most important takeaways for someone listening who's preparing for a technical interview, especially maybe for a senior role where design patterns really matter?
Okay, the essential takeaways are: first, the observer pattern offers a flexible and, crucially, loosely coupled approach to managing one-to-many dependencies. It enables automatic updates between subjects and observers without them needing explicit knowledge of each other's concrete types.
That decoupling.
That decoupling, yes. It's a fundamental principle for designing systems that are resilient to change, easy to extend, and highly maintainable. Our weather station example and the initial spreadsheet chart analogy vividly illustrate this. Understanding when and why to use this pattern really demonstrates a solid grasp of architectural principles.
Right, it's all about that crucial separation of concerns. The component that holds the data doesn't need to have specific knowledge of all the various ways that data might be consumed or displayed downstream.
Precisely. Second takeaway. It's critical to be aware of the trade-offs. Remember the potential for unexpected or unnecessary updates, cascading effects, spurious updates. And you need to understand the different implementation choices available, push versus pull models, how to manage observer lists, the role of a change manager in more complex scenarios. Being able to discuss these trade-offs shows a deeper level of understanding beyond just, reciting the pattern's definition from a book.
So it's not just about being able to name the pattern, but also about demonstrating an understanding of its practical implications, its costs and benefits, and when it's truly a suitable solution versus maybe a simpler approach.
Exactly. And that leads to the final point, maybe more of a prompt for the listener. For that listener gearing up for their technical interview, here's a final thought to ponder. Think about a system you've actually worked on, or maybe a common software problem you're familiar with. How could you apply the observer pattern there? Could it improve the design? Could it address potential future changes or extensions more elegantly?
Applied to their own experience.
Yes. Walking through a concrete scenario from their experience and being able to articulate the specific benefits and potential drawbacks in that specific context will not only solidify their own understanding, but also provide compelling and insightful talking points during an interview. Don't just talk theory. Talk application.
That's great advice.
And maybe push it further. Consider how you might handle a situation with multiple layers of dependencies. Would a simple observer work? Or would you start thinking about something more sophisticated like a change manager? Exploring those kinds of what-if scenarios and design justifications will really set you apart.